Students, in the previous lecture, we have derived some inequalities of trigonometric function with the help of geometric relation. Now we will derive some standard rules on limits. They are prove that limit x equals to 0 of sin x is 0, limit x is 0 of cos x is 1, and limit x is 0 of tan x is 0. To improve first result, limit x is 0 of sin x is 0 using definition. So in this fx, if you compare this function with the definition, fx would be sin x and L is 0. A in this case would be 0. So we'll find relation delta and epsilon. Now in this case, given epsilon, how small, we'll choose epsilon to be lying between 0 and epsilon pi by 2. 0 less than epsilon less than pi by 2. Not from between right and nothing. So for if your 0 is less than, we have derived this result. When 0 is less than modulus of x is less than pi by 2, we know that modulus of sin x is less than modulus of x. Now we have chosen epsilon to be less than pi by 2. Therefore, and now here modulus x is less than pi by 2. So if this relation is less than epsilon, and we take the epsilon to delta. Epsilon to delta means epsilon is lying between 0 and pi by 2, and x is also lying between is less than, so modulus x is also less than pi by 2. So this is the relation delta and epsilon. This we have fixed because this is given. And now why we do this? Because in the definition, when x is 0 means 0 is less than modulus x minus 0 is less than pi by 2, and sine of x minus 0 is less than x minus 0 is less than epsilon is equal to delta. So by using this, we can convert this into definition form. Now, given epsilon greater than 0, how small, there exists a positive real number delta is equal to epsilon, such that modulus of sin x minus 0 is less than epsilon. From here, modulus x equal to delta to epsilon, modulus sin x minus 0 is less than epsilon. For 0 is less than x minus 0 modulus is less than delta. So if you this can be written as x minus 0 is less than delta. So given epsilon over this, 0 less than epsilon less than 2, then these both the relations, this gives us both the relations holds true. This means sin x minus 0 is in that epsilon for 0 is less than x minus 0 modulus is less than delta. So this implies, what the meaning of this? This implies limit x equals to 0 of sin x is 0. Now, second calculate. We have to prove that limit x is 0 of cos x is 1. So for that, we made a substitution. We use the formula cos x is equal to cos x by 2 minus sin x is equal to 12. We have given the trigonometric. Replace cos x by 1 minus sin square x by 2. We got cos x equal to 1 minus 2 sin square x by 2. We know this because we want to use the function cos z. So then we replace cos x by 1 minus 2 sin square x by 2. Limit x is 0. Limit of the sum is sum of the limits. So limit x is to 0 of 1 minus 2 constant outside. Limit x is to 0 of sine of x by 2. This holds case. So as x is 0, x by 2 also equals 0. It's very small, x by 2 is also very close to 0. When x is very close to 0, x by 2 is also very close to 0. So replace x by 2 by x by x equal to 0 by x equal to 0. So now this become cos over this. So this is the limit of 1 is 1 minus 2 into limit x by t to 0 of sin x equal to this become 0. We have first result whole square. So this whole square will be 0. 1 minus 2 to 0, 0. So 1 is equal to 5 times 0. Similarly, now we want to prove limit x is 0 of limit x is equal to 0. This is again equal to, you take left hand side, is equal to limit x is 0 of sine and cos, limit of quotient limit. So limit x is 0 sin x, limit cos is 0 cos x. Limit x is 0 sin x is equal to, we proved it, 0, limit cos is 0 of limit x is 0 of cos x is equal to 1. 0 to 0, so now we then again type some results. Limit, prove that limit x is a of sin x is equal to a is a real number, and limit x is to a of cos x is equal to 1. So in order to write this, let us do the first word. Limit x is 0, x approaches to a of sin x is equal to limit x is 2, we make a substitution x is equal to a plus h. So I just approaches to a is equal to 0, x will approach 0 from positive always. So making the substitution, replace x by a plus h. Limit x is to a of sin x is equal to limit x is 0 of sin of a plus h. Using sin of a plus b here, sin of a will be sin a or b plus cos a sin b. Now limit of the sum, now limit of the sum is equal to limit of the sum is equal to sum limits. Limit of the sum limits and limit of product limits. Constant is taken outside the limit, therefore this is equal to, if it's, this is equal to limit constant outside, limit x is 0 of cos of h plus constant outside cos a, limit x is 0 of sin x. So limit x is 0 of cos x is 1, limit x is 0 of sin x is equal to 0. Sin of a is 1 plus cos equal to 0 is equal to sin of a is equal to right hand side. Similarly, you can prove limit x is 0, x equals to a of sin of, so cos of x equal to cos of a. Same substitution as we did in the sin of limit x is 0, x equals to a of sin x. We make substitution x is equal to a plus h, as x equals to a, therefore equals to 0. Improve this value. And next that is prove that limit x approaches to 0 of sin x upon x is equal to 1, and limit x is 0 of tan x upon x is equal to 1. Let's go first result. So in order to prove this result, we, we make this inequality which we proved in previous lecture. We know that modulus of sin x is less than modulus of x is less than x for x, for 0 less than modulus of x is less than I. Because of 2. Now this is inequality and there are positive numbers, modulus the positive number. Divide the inequality by sine of x, sine of modulus x is positive number. If you divide the inequality by sine of modulus x, sine cancel, this modulus sine x and modulus x, and modulus sine x is less than sin x upon, then equation of sin and cos, modulus product and quotient is quotient of modulus, or sin x upon modulus cos x up into 1 upon modulus sin x. Sin is cancelled. So we got 1 is, this implies 1 is less than equal to less than modulus x upon modulus of a upon modulus of b modulus a upon b. Using this here. So 1 is less than modulus of sin x upon sin x is less than 1 upon 1 upon cos x. Now this is, now if you see this, in this, if 1 by 3 is less than 1 by 2 is less than 1, Therefore, 3 is greater than 3 is greater than 2 is greater than. So reverse this inequality using this. We get positive numbers. We have all positive numbers. Positive numbers using this. Reversing the inequality, the positive numbers. Reversing this inequality will reverse. So therefore, cos x will be cos x will be less than modulus of sin x upon x is less than 1, or 1 is greater than sin modulus sin x upon x is greater than cos x. Or this is reverse out. Now we know this is fx, this is gx. Now sin x modulus of sin x upon x is equal to sin x upon x for x belonging to x belongs to minus pi by 2 to 0, you need the current. If x belongs to 0 to pi by 2, sin x is positive, x is positive, we get the same. If x belongs from minus pi by 2 to 0 interval, then sin x is minus modulus sin x is equal to minus sin x, modulus x is equal to minus cancel, and in this pi by 2 greater than the root of 0, we we can replace modulus sin x upon x by sin x upon x. So this is this. Now fx is less than gx is less than hx. The limit of fx as x equals 0 is equal to 1, and limit of constant 1 as x equals 0 is equal to 1. Therefore, the squeeze principle limit of fx is 1. G, you have to find the limit of gx and limit of x is 1. Therefore, squeeze principle limit x is 0 of sin x is also equal to sin x upon x is also equal to 1. Similarly, limit x is 0 of tan x, we have to prove we want to give limit to x is 0 of tan x square x is equal to 1. Convert this into sin inverse by taking left hand side. Convert this into sin and cos. Limit x is 0 of sin x upon x 1 upon cos x. Limit of product is the limits. Limit of sin x upon x x is 0. We have proved it earlier. It's equal to 1. And limit x is 0 of cos x 1 upon limit x is 0 1 upon limit x is 0 of cos x is equal to 1. 1 into 1 upon 1 is equal to 1. It's equal to 1 to right hand side. Now we do some corollary based on the results just now. Prove that limit x is to 0 of sin inverse x upon x is equal to 1, and limit x is 0 of tan inverse x is equal to tangent inverse x upon x is equal to 1. Positive limit x is 0 of sin inverse x upon x is equal to 1. Now we, by taking left hand side, we convert this into the formula sin x upon x, limit x is 0 to 1. So for that we make a substitution. Let us say, let's put sin of x is equal to theta, therefore x is equal to sin theta. So as x equals to 0, theta is equal to 0. So by taking this left hand side of the result, limit x to 0 of sin of x upon x, make substitutions is equal to limit theta to 0 of theta upon sin theta. So this can also written as a upon b upon c upon d is equal to 1 upon sin theta upon theta, limit theta to 0. Limit of quotient limits, limit of 1 is 1, limit of constant is same, limit of limit is equal to 1 upon limit x is 0 of sin x upon x is equal to 1.1. 1 upon 1 is equal to 1 is equal to right. So similarly, prove that limit x is 0 of tangent inverse x upon x is equal to 1. So same substitution here. You know this inverse function. Put tangent inverse x is equal to theta. So therefore x is equal to tan theta. As x equals to 0, x is 0, theta is 0. 0, theta is equal to 0. So left hand side taking left hand side, limit x equals to 0 of tangent inverse x upon x is equal to the substitution here. Theta upon limit x is 0, theta upon sin theta. This can also written here a upon b upon c upon d is equal to limit 1 upon tan theta upon theta, limit theta to 0. Limit the quotient limit. percentage, percent limit, limit theta approaches 0 of 1 is 1, limit of